Is on congruence mod n. Recall that if we have two integers m and n, then n divides m if m is equal to n times k for some integer k. So for example, 2 divides 6 because 6 is equal to 2 times 3, where 3 is an integer. So here's our new definition. Given integers a and b and a natural number n, a and b are congruent mod n if n divides a minus b. This is denoted in several different ways. So this is denoted a is congruent to b mod n or modulo n. It's also written as a is congruent mod n to b. So for example, if we look at 17 congruent to 2 mod 5, we see that that is a true statement because if we look at a minus b, if we look at 17 minus 2, that's equal to 15, and 5 divides 15 since 15 is equal to 5 times 3, where 3 is an integer. So let's look at 2 other examples. I will let you pause and try these out. So true or false. True or false, 14 is congruent to negative 8 mod 6. And true or false, so 1, 2, negative 19 is congruent to 8 modulo 3. So try these both out, pause, and try each of those out, and we'll talk about them in just a moment. Okay, let's take a look at these. So we were asked to determine whether or not 14 and negative 8 were congruent mod 6, and so by the definition, we can look at 14 minus a negative 8. 14 minus negative 8 is a positive 22, and then we can say, okay, does 6 divide 22? No, 6 does not divide 22 because 22 is not equal to 6 times k for any integer k. So we see that this is a false statement. Now let's look at, does negative 19, or is negative 19 congruent to 8 modulo 3? We can do the same. Negative 19 minus 8 is equal to negative 27, and 3 does divide negative 27 because negative 27 is equal to 3 times negative 9, and negative 9 is an integer. So that tells us that this is a true statement because negative 19 is congruent to 8 modulo 3. You may have seen mod n in a different context before, and I wanted to address that. So mod is actually used in 2 different ways. The definition we're using, a and b are congruent mod n if n divides a minus b, or a is congruent to b mod n, is a statement. So this is a statement which, as we saw above, can be true or false. Whereas the other way you may have seen it, a mod n, is an operation. Sometimes that operation, especially in computer science, is denoted a mod n, and a mod n in that context is the remainder r when a is divided by n. So for example, 10 mod 4 is the remainder when 10 is divided by 4. So 10 divided by 4 gives us 2 because 4 times 2 is 8, and that's the closest we can get, with a remainder of r equals 2. So 10 mod 4 is 2, and just as one more example, 10 mod 3, for example, is 1, because the remainder when we divide 10 by 3 is 1. 3 goes into 10 3 times, with a remainder of 1. Where this gets a bit tricky is when a is a negative integer. So remember, the integers are positive and negative whole numbers as well as 0, whereas the natural numbers are just the counting numbers, 1, 2, 3, 4, etc. So what happens if a is a negative integer? For example, if we were trying to find negative 13 mod 4 or negative 13 mod 4, we'd have to think about what the remainder is when we divide negative 13 by 4. And just as a reminder when we're approaching this, let's look at the division algorithm. So the division algorithm states that if a is an integer and n is a natural number, then there are unique integers q and r such that a is equal to n times q plus r, where r is between 0 and n. So what's important here is that r is greater than or equal to 0 and less than or equal to n, the integer that's dividing. So with that in mind, let's look at negative 13 mod 4. So we're looking for the remainder when we divide negative 13 by 4. And according to the division algorithm, we know that negative 13 is going to be equal to 4 times some integer q plus some integer r, where r is between 0 and 4. So 0 is less than or equal to r, which is less than or equal to 4. So we have negative 13 is equal to 4 times something plus a non-negative value. So that means that what we have here has got to be less than or equal to negative 13 because we're adding a non-negative value to it. So we have to use negative 4 here as the integer that it would get us closest to negative 13. So negative 13 is equal to negative 16 plus what? Well, plus 3. So that tells us that r is equal to 3. So that is the remainder when we divide negative 13 by 4. And so negative 13 mod 4 is equal to 3. Okay, so using this definition of a mod n, let's find 2 more examples. So let's find 16 mod 4, and let's also find negative 23 mod 5. So pause, take a look at that, and we'll talk about it in just a second. All right, so 16 mod 4. So 16 is equal to n times q plus r, in this case 4 times 4 plus 0, where the remainder 0 is, of course, less than or equal to 0 and less than or equal to 4. So 16 mod 4 is 0. 0 is the remainder when we divide 16 by 4. And if we look at negative 23 mod 5, then we could say, all right, negative 23 is equal to 5 times something plus r, where 0 is less than or equal to r, which is less than or equal to 5. So what values could make sense for r and q? So negative 23 is equal to 5 times some integer such that we are adding a non-negative integer to this to make it equal. So 5 times what could we use? We could use negative 5, and that means that r has to be equal to positive 2. So negative 23 is equal to negative 25 plus 2, and so r is equal to 2, the remainder is 2, and therefore negative 23 mod 5 is 2. Okay, so we have these 2 different uses of the term mod. We know that a is congruent to b mod n if n divides a minus b, and again, this use of a congruent to b mod n is a statement. It can be true or it can be false, whereas a mod n is an operation, and it is the operation what is the remainder r when we divide a by n. So these two different uses of mod do have a relationship between each other, and the relationship is this. A is congruent to B mod n if A and B each have the same remainder when divided by n. So if A mod n is equal to R and B mod n is equal to the same remainder R. So that is if A and B have the same remainder when divided by n. So this is actually an if and only if statement. So for example, negative 12 is congruent to 8 mod 5. We could see this using either definition of congruence mod 5. One way we could see that is because using the original definition, negative 12 minus 8 is equal to negative 20, and 5 divides negative 20 since negative 20 is equal to 5 times negative 4, and negative 4 is an integer. The other way we could see this is by looking at negative 12 mod 5 and also looking at 8 mod 5. So negative 12 mod 5 is, negative 12 is equal to 5 times some integer q plus some integer r, where 0 is less than or equal to r, which is strictly less than 5. So what values of q and r would work there? Negative 12 is equal to 5 times negative 3 plus a positive 3. Negative 12 is equal to negative 15 plus 3. So r is equal to 3, and therefore negative 12 mod 5 is 3. Now we can also consider 8 mod 5. 8 is equal to 5 times 1 plus 3. So 8 mod 5 is also 3. And because 8 mod 5 is 3 and negative 12 mod 5 is 3, because they are equal, that implies that negative 12 is congruent to 8 mod 5.